Welcome back to Automata Theory. In this lecture we will discuss pushdown automata. We've seen that finite automata give rise to the class of regular languages. Finite automata have no memory except for the current state, and they have only a finite number of states. So finite automata cannot accept languages like a to the n, b to the n, where you need some kind of counting to make sure that there's as many a's as b's. So our next goal is to find a class of automata that corresponds to the context-free languages, so that can accept languages like a to the n, b to the n. And the idea is to equip automata with a stack. And the stack has an unlimited size, so it can be used to perform things like counting. So next to our input alphabet sigma, the automata now also have a stack alphabet gamma. And what's a stack? A stack is just as you imagine, you stack things on top of each other. And the crucial property of a stack is that you can only add and remove elements from the top of a stack. So we can add things on top and remove from the top. For instance, we could remove the D here, but we cannot remove the A from the bottom. We will write stacks as words, and we will write them with the topmost element on the left. So this stack ABCD would be written as DCBA. D is the topmost element, A is the bottom element on the right. Now our pushdown automata that work with a stack, they are basically an extension of nondeterministic finite automata. They also take in the transition function the state as an input of the transition function, the input letter or a lambda transition. So this part is just the same as for nondeterministic finite automata, but the transition function additionally inspects the topmost element on the stack. And now the transition function gives us as result a possible choice of states to switch to and a word over the stack alphabet. That's the new elements that we add on top of the stack. The element that we inspect on the stack gets removed, and the elements that are given here are added back on top of the stack. So it switches the state and it adds 0 or more elements on top of the stack. This nondeterministic choice, in principle, this is the power set of q times gamma star. This could be an infinite power set, but we don't want this. We are speaking here about finite pushdown automata. So we want that this nondeterministic choice here is always finite. So there's a finite choice of what states to switch to and what words to add back on top of the stack. A nondeterministic pushdown automaton, short NPDA, is a tuple that consists of the following ingredients: a finite set of states Q, a finite input alphabet sigma, a finite stack alphabet gamma. So this is new, this was not part of nondeterministic finite automata. We have a transition function that we've just discussed on the last slide. The nondeterministic choice, so when we apply the transition function delta to a state, an input letter or lambda, and a stack symbol b, then this set given by the transition function should always be finite. So there should always be a finite choice of what to do. We still have a starting state, and in general nondeterministic automata could have a set of starting states, but for finite automata we've already shown that a set of starting states is equivalent to just a single starting state. So for the nondeterministic push automata, we just take a single starting state. We now also have a stack starting symbol. Initially, when we start the automaton, this will be the entire stack content. So the stack will initially just have the symbol Z. And we still have a set F of final states. Now, how should we understand this transition function? If we have that Q prime V is in delta Q alpha B, so Q is a state, alpha is a letter from the input alphabet or lambda, B is a stack symbol. This means that if the automaton is in state Q and the input is alpha W and the stack content is BU with B the topmost stack symbol, then the automaton can do a transition to the state Q prime with input W, so alpha is consumed. If alpha is the empty word, then nothing is consumed. And the stack symbol B is replaced by V. So V are the new elements added on top of the stack. If V is empty, then B is just removed, and otherwise B is replaced by one or more new symbols on the stack. A configuration of a non-deterministic pushdown automaton is now a triple QWU, where Q is a state of the automaton, W is an input word, so from sigma star, and U is the current stack content, a word from gamma star. Now, as explained on the last slide, we have steps of this automaton. So we have a step relation defined on configurations. From a configuration Q alpha W BU, we have a step to Q prime W VU whenever Q prime V is in delta Q alpha B. So if the transition function tells us that from state Q with input letter alpha or lambda and topmost stack symbol B, we can switch the state to Q prime while replacing the topmost stack symbol B with V. And that's exactly what happens in this step. The state changes from Q to Q prime. The input letter alpha is consumed. If alpha is lambda, nothing happens. And B on the stack is replaced by V. As before, we write this turnstile symbol to the star for a sequence of steps, 0 or more steps. And we will refer to this as a computation of the pushdown automaton. Now, the language generated by a non-deterministic pushdown automaton consists of all those words over the input alphabet, such that there is a computation of the following form. Namely, if we start our pushdown automaton in the starting state with the input word W, so that's the input word that we're considering, and the initial stack content just consisting of Z, then there is a computation that brings us to a final state, Q prime. The input has been completely consumed, so nothing is left of the input, and the stack content can be arbitrary. So all we require is that started in the starting state with the input word and stack content Z, there is a computation that brings us to a final state while having consumed all the input. There is no condition on the stack content for the language of the NPDA. We want to draw our pushdown automata also nicely visual as transition graphs, just as we have done for finite automata. So now in the transition graphs we will write arrows of this form. So we have an arrow from a state Q to Q prime with this label. So the label is alpha and then in brackets B/V. This means if our input is alpha and on the top of the stack we have B, then we can take this transition. And in this transition, so the state switches from Q to Q prime, and on the stack we are going to replace B by V. So let's try this out. Let's construct a pushdown automaton for the language a to the n, b to the n for n greater or equal 0. So we will do this as follows. We will use states Q0, Q1, Q2. We have the input alphabet AB. Our language consists of A's and B's. we will use as stack alphabet 0 and 1. As stack start symbol we use 0, so initially there will be just a 0 on the stack, and we use Q2 as our only final state. Now we will use the following intuition, namely if we are in state Q0, then a stack content of the form 1 to the k 0, that means that 0 is at the bottom and then there's k ones on top. This means that we have seen KAs, we have read KAs. And in the state Q1, this stack content of the form 1 to the k0 will mean that we still have to read KBs. So the number of ones tells us how many A's we have seen or how many B's we still have to read. So let's start. So we have our starting state Q0. Now let's try to implement this intuition. For every A that we read in Q0, we want to add a 1 on top of the stack. So initially there's a 0 on the stack, our stack start symbol. So we need the transition of this form. It says if we read an A, and if there's a 0 on the stack, then we replace the 0 by 1 0. So that basically means we leave the 0 on the stack and we add a 1 on top. Now, after having taken this transition, there's no longer a 0 on the top, now there's a 1 on the top. So we need one more transition on our state Q0. We also need to specify what happens if there's a 1 on top of the stack. So this transition now says, if the input is an A, and if there's a 1 on top of the stack, then we put an additional 1 on top of the stack. Okay, so for every A, we put an additional 1 on top of the stack. Now, when do we start removing ones? We start removing ones when we read a B. So if we see a B, then we switch to state Q1. We say that if the input is B, and if there's a 1 on top of the stack, then we replace this by lambda. So we remove the 1 from the stack. We don't replace it by anything. And we want to continue reading B's as long as we have ones. So as many B's as we have ones on the stack. So we continue in Q1. We say that if we read a B, then as long as there's a 1 on the stack, we can read a B, and we remove the 1. Now, when do we switch to our final state Q2? We switch to our final state Q2 as soon as all the ones are removed. So if there's a 0 on top of the stack, then we know we have read as many B's as A's. So then we switch to Q2, our final state. We do this without consuming any input. We just require that there's a 0 on top of the stack. So at this point, when there's a 0, we know that we have read as many B's as we have A's. Because for every A, we've added a 1. For every B, we've removed the 1 from the stack. So if all the 1s are gone, then we have a word of the form A to the n, B to the n. So we can switch to the final state and we remove 0 from the stack. So we empty the stack. This is not so important because we don't have a condition on the shape of the stack at the acceptance. So we could also leave the 0 on the stack at this point. It wouldn't change the language of the automaton. But anyway, we remove the 0 here and we are almost done. There's one word that we cannot accept yet, and that is if n is 0, the empty word. We also have to be able to accept the empty word. That means we have to be able to accept immediately, so we add an additional lambda transition from Q0 to Q2. So also from Q0 to Q2, we say that without consuming any input, we can simply remove the 0 from the stack and we switch to Q2. Using this transition, we can accept the empty word. Once we have read an A, there's no longer a 0 on top of the stack. There's a 1, so then we have to take this transition reading a B in order to get to an accepting state. Now let's have a look at this automata in action. We now start this automaton on the following configuration. So that's a starting configuration with our starting state. The input is AABB and the initial stack content is just the stack starting symbol 0. Now what's the first step that the automaton does? We are in state Q0. we have a letter A in the input. So it's either this or this transition or the lambda transition. So we could in principle also take at this point the lambda transition. This transition is enabled. We're on state Q0. We don't need to consume any input. There is a 0 on top of the stack. So we could take this transition. However, then in Q2 we cannot read any input anymore. So there's no way to get from Q2 to a state where we have consumed all the input. So this would not be an accepting pass. So if we want to accept this word, we have to consume this entire word. So we have to read the A using this transition or this transition. So we have a 0 on the stack. That means that we can only choose this transition. We have input letter A, 0 on the stack. We consume the A and we replace the 0 by 1, 0. So we stay in state Q0, 1A is consumed, and the stack content is now 1, 0. Now we are in state Q0, input letter is again A, but now on the stack we have a 1. So we have to take this transition. We have an input A 1 on top of the stack, and we replace the 1 on the stack by 1, 1. So this gives us, we're still in state Q0, we have consumed the second A, we have now BB as input, and the 1 is replaced by 1, 1. Now we are in state Q0, we have a 1 on the stack and input letter B. So the only transition that we can take is this transition with input B and the 1 on the stack. The 1 is removed from the stack, the B is consumed, and we switch to Q1. So we are now in Q1, we've consumed 1B, and we've removed the topmost 1 from the stack. Now we are in Q1, we again have a 1 on the stack and an input B. So we cannot take this transition because we have a 1 on the stack. So the only transition that we can take is this one. We consume the input letter B and we remove the 1 from the stack. Now we are in state Q1, we have consumed all the input and we have just 0 on the stack. This means that now we can take only this transition. The lambda transition does not consume any input, but it removes the 0 from the stack. So we get to Q2 with an empty input and an empty stack. So the word AABB is in the language accepted by this automaton because we've started in the starting state with the input word, with the stack just containing the stack start symbol, and we have a computation that has brought us to a final state while having consumed all the input. And again, it's not so important that the stack is empty here. The only important thing is that we are in a final state while having consumed all the input. So what can we do if we want to change the automaton in such a way that instead of a to the n, b to the n, it accepts the following language, namely a to the n, b to the 2n. So twice as many b's as a's. I think the idea is quite obvious. We add 2 1s for each a that we read. So this is basically the same automaton as we've seen on the previous slide, but instead of adding a single 1 for every a, we add 2 1s on the stack for every a. So if there's a 0 on the stack, we replace it by 1 1 0. If there's a 1 on the stack, we replace it by 1 1 1. So 2 additional 1s for every a. And then the rest of the automaton is unchanged, meaning that we have to read 1b for every 1 on the stack. Since we've added 2 1s for every a, it means that we have to read twice as many b's as a's, giving rise to the language a to the n, b to the 2n for n greater or equal 0. In this exercise, we are asked to construct a non-deterministic pushdown automaton that accepts this language. So it consists of all words of the shape w reverse for a non-empty word w over ab. So this is particular palindromes. So this is palindromes of even length. The idea is that we use an automaton consisting of 3 states. Our input alphabet is clearly just AB. As stack alphabet, we use AB and Z, where Z is our stack start symbol. So the idea is that we use A's on the stack to remember that we've read an A. We use B's to remember that we've read an B. So whenever we read an A, we will put an A on the stack. If we read a B, we will put a B on the stack, at least for the first part of the word. And if we enter the second part of the word, then we will remove A's and B's from the stack. Our accepting state is Q2. So now let's begin. We have our starting state Q0, and now we assume that we are reading this first part of the word. So then we want to put the word that we've read on the stack. So if we read an A, we want to put an A on the stack. And there's actually 3 different cases to consider here. There could be an A on the stack, a B on the stack, or a Z on the stack. And we have to give a transition for each of them. So if we read an A, then if there's a Z on the stack, we leave the Z and we put an A on top. If we read an A and there's already an A on the stack, we put another A on top. If we read an A and there's a B on the stack, we put an A on top of the B. So in each case, we put an additional A on top of the topmost stack symbol. And similarly, we do this if we read a B. If we read a B, we put a B on top of the stack, additionally to the symbol that was already on top of the stack. So if there was a Z, we put a B on top of the Z. If there was an A, we put a B on top of the A. And if there was already a B, then we put one more additional B on top of the stack. So what do we have after reading a word? We have this word in reverse on top of the stack. And now if we enter the second part, we want to read W in reverse, then we can just do this by requiring that we read an A if there's an A on top of the stack. So we say if there's an A on top of the stack, we can read an A and we remove the A from the stack. If there is a B on the stack, then we can read B and we remove at the same time the B from the top of the stack. So this transition switches from reading the first part to starting to read the second part. So this transition reads the first letter of the second part. We are now reading the word that we have read in the beginning in reverse. In Q1 we continue the same thing. We say that if there's an A on the stack, we can read an A and we remove the topmost stack symbol. If there's a B on the stack, we can read a B and we remove the topmost stack symbol. And as soon as we have read all the word that we have read in Q0 in reverse, then all the A's and B's are removed. So then there's again a Z on top of the stack. Then we can switch to Q2 and accept. So if there's a Z on top of the stack, then without consuming any input, we remove the Z and we switch to an accepting state, Q2. So this automaton will accept all words of this form. This first part W is read in Q0 and we basically add W on top of the stack. Each letter of W we add on top of the stack while we read it. And then when switching to Q1, we start popping the symbols from the stack and we require that we always read precisely those symbols that match the symbol that was on the stack. This makes sure that in the second part here, we read the word that we've read in the first part just exactly in reverse. And as soon as we've read the entire first part in reverse, we switch to an accepting state, Q2. Now this exercise asks whether there is an NPDA that accepts the language WW for W, a non-empty word, over AB. We've just constructed a non-deterministic pushdown automaton for the language WW reverse. But now the question is, can we also do it with the second part not reversed, but repeating exactly the first part? And the answer to this question is, it's not possible. We cannot do this with a non-deterministic pushdown automaton. intuitively, the reasoning is as follows. If we read the first part W, then we add the symbols of W on top of the stacks. But then the last symbol that we have read from W is on top of the stack. So if we pop these symbols, then we have to pop them in reverse. So we cannot make sure that the word that follows is the same as the word that we have read. In order to do this, we would have to inspect the bottom symbol of the stack. We would have to remove symbols from the bottom of the stack. And that's not possible with a stack. We will later see that this language, WW, so this square words, is indeed not a context-free language. And we will prove this using the pumping lemma for context-free languages. So indeed, for this language, there cannot be a context-free grammar, and there cannot be a non-deterministic pushdown automaton. In the literature, non-deterministic pushdown automata are sometimes defined with a different acceptance condition. They do not accept in final states, but they accept when the stack is empty. All the non-deterministic pushdown automata that we've seen so far had the property that they reach a final state if and only if their stack is empty. In the literature, the emptiness of the stack is often also used as an acceptance condition for NPDAs. So in the literature, one often finds this definition as the definition of the language of an NPDA. We will refer to it as the empty stack language of the non-deterministic pushdown automaton M, in order to distinguish it from the language of the non-deterministic pushdown automaton, which in our case is defined via acceptance in final states. So the empty stack language of a non-deterministic pushdown automaton, denoted by L lambda of M, consists of all words W over the input alphabet, such that if we start our non-deterministic pushdown automaton in the starting state with the input word W and the stack content just the stack starting symbol, there exists a computation that brings us to some configuration that has consumed all the input and the stack is empty. So there's no condition on the state that we are reaching. It does not need to be a final state. The only condition is that we've read all the input and the stack is empty. If we are using this definition of the language of a non-deterministic pushdown automaton, then in principle we don't need to include the final states in the definition of an NPDA. So in the literature you often find this condition, acceptance with an empty stack, and we will show that this is equivalent to acceptance in final states. Consider the non-deterministic pushdown automaton shown on this slide. What is the language accepted by this automaton? The automaton is started in state Q0. If you read an A, the stack starting symbol is replaced by a 1. For every additional A that we read, we add an additional 1 on top of the stack. We can read the B if there's a 1 on the stack, and then we remove this 1. So the B can be read only after having read at least one A. Then, after having read a B, we can immediately accept, but we can also continue reading B's, and for every B, we remove one 1 from the stack. So we can read at most as many B's as we have read A's before. So the language of this automaton is of the form A to the n, B to the m, so all the words of the form A to the n, B to the m, such that we have at least as many A's as we have B's, so n is greater or equal than m, and we must have at least one A and one B, so n and m must be at least 1. Now what is the empty stack language of the same automaton? The stack is empty only after having read as many B's as we have read A's before. So the empty stack language is of the form A to the n, B to the n for n greater or equal 1. So this example shows that the language of a non-deterministic pushdown automaton defined via acceptance in final states can be different from the empty stack language defined via acceptance with an empty stack. However, both definitions, acceptance via final states and acceptance via empty stack, are equally expressive. So they both give rise to the same class of languages. And we will show how one formalism can be transformed into another. So we will show how we can take a non-deterministic pushdown automaton and we can transform it into a new non-deterministic pushdown automaton such that the empty stack language of the new automaton is equal to the language of the old automaton, and reversely. First, we're going to look how acceptance in final states can be transformed into acceptance with an empty stack. Every non-deterministic pushdown automaton M can be transformed into a non-deterministic pushdown automaton N, such that the language of N is the same as the language of M. Moreover, N has a single final state. This final state is reached if and only if the stack is empty. And this property means that the empty stack language of N is the same as the language of N. So for N, acceptance in an empty stack is the same as acceptance in a final state. Thus, in particular, the empty stack language of N is equal to the language of M. So how do we obtain such an automaton N? We start from M and we add 3 fresh states, Q0 hat, QE, QF, and we add a fresh symbol Z hat to the stack alphabet. Now we add transitions to our automaton. From Q0 hat, we add a lambda transition to the old starting state Q0. And what does this lambda transition do? It does not consume any input, but it adds this fresh stack symbol Z hat to the bottom of the stack. And the intention here is this is a fresh stack symbol, so the old automaton cannot remove it from the stack. So the old automaton cannot empty the stack anymore, but the old automaton can still do the usual operation on top of Z hat. Now, from every old final state Q, we add a lambda transition to the fresh state QE, and this lambda transition keeps the stack unchanged. So for every stack symbol S, we have a transition that does not consume any input. It inspects S on top of the stack and it leaves S on top of the stack. So this transition basically doesn't change anything except for the state, from an old final state to QE. And now QE is responsible for emptying the stack. So for every stack symbol S except for Z hat, so except for this fresh stack symbol, we have a loop on the state QE, and this transition does not consume any input, and it removes the symbol S from the top of the stack. So by taking this loop on the state QE, we can remove all symbols from the stack except for Z hat. And finally, once the stack is empty except for Z hat, we have one more transition that goes to our new final state QF, so it does not consume any input. It removes Z hat. So when we switch to QF, the stack is really empty. And now we make Q0 hat our new starting state and QF our only final state. And we have obtained an automaton that reaches this final state if and only if the stack is empty and otherwise simulates the behavior of our original automaton M. This transformation is best understood by means of an example. Here we have our non-deterministic pushdown automaton M, and we will transform it into a non-deterministic pushdown automaton N, for which the empty stack language is the same as the language, and this language is the same as the language of our original automaton M. We start with our original automaton, and we add 3 fresh states. From our new initial state Q0 hat, we add a transition to our old starting state Q0. This transition does not consume any input, and it replaces the stack start symbol Z by ZZ hat. So now Z hat is on the bottom of the stack. And since Z hat is a fresh symbol, the old automaton cannot remove it from the stack. So the old automaton cannot empty the stack. Now, the old automaton can do the same computation as before, and if it reaches a final state, we want to empty the stack. So from every final state of the old automaton, we will add transitions to the state QE, which will then empty the stack. So we want to enable this transition from a final state to QE, no matter what is on the stack. So we add transitions from every final state and for every stack symbol. In this case, we have only one final state, but we need transitions for every stack symbol. So these transitions don't consume any input. And no matter what is on the stack is left unchanged. So in this case, we have stack symbols of the original automaton Z and 1. And we have a fresh stack symbol Z hat. So we need 3 transitions. One that checks whether there's Z on the stack and it leaves it on the stack. One for Z hat and one for the stack symbol 1. So no matter what is on the stack, we can switch from a final state to QE. And now QE is responsible for emptying the stack. So QE can remove any stack symbol except for the new stack symbol Z hat. So we again have transitions that don't consume any input. They remove Z from the stack and 1 from the stack. And we can repeat this until the stack is empty, until there's only the new symbol Z hat left on the stack. And since we know that Z hat is on the bottom of the stack, as soon as we reach Z hat, we are sure that if we remove Z hat, then the stack is empty. So we add one more transition from QE to QF that checks whether Z hat is on the stack, it removes it from the stack, and then we know the stack is empty. The only thing that remains to be done is we declare QF as our only final state. Now we have obtained an automaton that can reach the final state QF if and only if the stack is empty. And that means that the empty stack language of this new automaton is the same as the language of the new automaton. And by construction, the language of the new automaton is just the same as the language of the old automaton. Now we will show that also acceptance with an empty stack can be transformed into acceptance with final states. For every non-deterministic automaton M, we can construct a non-deterministic automaton N such that the language of the new automaton is equal to the empty stack language of the old automaton. Moreover, the new automaton has a single final state, and this final state is reached if and only if the stack is empty. So the empty stack language of the new automaton is equal to the language of the new automaton. So how does this construction work? We start with the old automaton and we add 2 fresh states, Q0 hat and QF, and we add a new element to the stack alphabet, Z hat. Now the first idea is similar to the construction before. We add the transition from Q0 hat to our old starting state Q0, and this transition puts Z hat on the bottom of the stack. So we again have a marker for when the stack is empty. Moreover, we add transitions from every state of our old automaton to our new final state QF, and the condition for taking this transition is that there's Z hat on top of the stack. So in other words, it means that the stack is empty except for Z hat. And finally, we say that Q0 hat is our new starting state and QF is our only final state. Again, this construction is best understood by means of an example. Here we have our non-deterministic pushdown automaton M, and we are going to transform it into an automaton N, for which the empty stack language is the same as the language, and the language is the same as the empty stack language of our original automaton M. So we start by taking M and we add 2 fresh states. From our new starting state Q0 hat, we add the transition to Q0, and as before, this transition puts on the bottom of the stack the symbol Z hat. So we have now a marker for recognizing when the stack is empty. And this marker cannot be removed by the old automaton because the old automaton doesn't know Z hat. Now we add transitions to our new final state QF from every state of the old automaton. So from Q0 and from Q1. And these transitions do not consume any input. The condition is that Z hat is the topmost stack symbol. That means the stack is empty except for Z hat. And if we remove Z hat, the stack will really be empty. And one more transition from Q1. And finally, we have to say that QF is our only final state, and we are done. So now we have an automaton whose final state can be reached if and only if the stack is empty, and this automaton accepts the same language as the empty stack language of the original automaton. We can switch to the final state here if and only if the stack of the old automaton was empty. Next, we will see that the class of languages accepted by nondeterministic pushdown automata is precisely the class of context-free languages. So a language is context-free if and only if there exists a nondeterministic pushdown automaton that accepts this language. And in order to prove this, we have to prove again 2 directions. We have to show that we can translate context-free grammars into equivalent nondeterministic pushdown automata. So here equivalent means that the language accepted by the nondeterministic pushdown automaton is the same as the language generated by the grammar. And we have to show that we can translate nondeterministic pushdown automata into equivalent context-free grammars. We start with the translation of context-free grammars into nondeterministic pushdown automata. So let G be a context-free grammar with variables v, terminals t, start symbol s, and production rules p. Now the idea is we create a nondeterministic pushdown automaton that simulates a leftmost derivation of the grammar using the stack. Our automaton will have states Q0, Q1, and Q2. Q0 is our starting state, Q2 is the only final state. The input alphabet of our automaton are the terminal letters. The stack alphabet consists of the variables, the terminals, and a fresh symbol Z. We have the following transitions. From our starting state Q0 to Q1, we have a transition that does not consume any input. It just puts the starting variable S on top of the stack. Z, the stack start symbol, remains on the bottom of the stack. Now we have 2 transitions from Q1 to Q1. The first one allows to simulate the rewrite steps of the grammar. It does not consume any input, but it says if we have a variable a on top of the stack, then we can replace this variable a by x. If there's a rewrite rule, a rewrites to x in our grammar. So you see here that the grammar says a can be rewritten to x, so a can be replaced by x, and exactly that's what happens on top of the stack. A is replaced by x. So this simulates a rewrite step of the grammar on top of the stack. These transitions allow us to read an input letter A if there is this input letter, the terminal A, on top of the stack. So if there's a terminal A on top of the stack, then we can read A from the input, and we remain in Q1. And finally, we have a transition from Q1 to Q2. We can take this transition without consuming any input, but only if there's Z on top of the stack, and we empty the stack and switch to our final state, Q2. And then it can be shown that the language accepted by this automaton is the same as the language generated by the grammar. Let's have a look at an example. Here we have a context-free grammar. This grammar generates all words of the form WWR, where W is a non-empty word. We want to transform this grammar into a pushdown automaton that accepts the language generated by this grammar. This pushdown automaton has 3 states, Q0, Q1, Q2. Q0 is our starting state, Q2 is the only final state. From Q0 to Q1 we have a transition that does not consume any input, and it just adds an S on top of the stack. From Q1 to Q1 we have transitions for every rule of our grammar. We have 4 rules of our grammar, so we get 4 transitions from Q1 to Q1. These transitions don't consume any input, but they simulate the application of this grammar rule on the stack. So the grammar rules say that we can replace S by ASA. Likewise, this transition says we can replace S on top of the stack by ASA on top of the stack. And similar we have for this rule, this transition, for this rule, this transition, and for this rule, this transition. Now all these transitions do not yet consume input. We still have to somehow read our input word. For this we have 2 transitions because we have 2 letters in our input alphabet, A and B. If we have a terminal letter A on top of the stack, then we can consume an A from the input and remove A from the top of the stack. Likewise, if we have a B on the top of the stack, we can read an B and remove B from the top of the stack. Once the stack is empty, so there's only the stack start symbol Z left on the stack, we can switch to Q2. And we empty the stack, we remove Z from the stack. So this automaton accepts the language generated by this grammar. Let's have a look. This grammar generates the word ABBA, so the automaton should be able to accept this word. How does the grammar generate this word? It's one application of the first rule followed by an application of the last rule. So now we start our automaton in our starting state Q0 with the input ABBA, and the stack consists just of the stack start symbol Z. So we take this transition which adds the starting variable S on top of the stack. Now we have an S on top of the stack, so we have a choice between these 4 transitions. We should use this transition. We should replace the S by ASA because this is the step that corresponds to the grammar rule that generates this word ABBA. So we use this transition, we replace the S by ASA on top of the stack. So now we have ASA on top of the stack. The topmost stack symbol is A, and we have input. The first letter of the input is an A as well, so we can apply this transition which consumes the input letter A and removes the topmost A from the stack. Now we have again S on top of the stack, so we again can choose between these 4 transitions. We have to choose this transition because we want to replace S by BB on top of the stack. So now S gets replaced by BB on top of the stack. Now we have a B on top of the stack and a B in the input. We use this transition which consumes a B from the input and removes B from the top of the stack. Now we have the same again, a B in the input and a B in the input and a B on top of the stack. So we again use this transition, removing the B from the top of the stack. Now we have an A on the input and an A on top of the stack. So we again use this transition, removing the A from input and stack. And finally we have consumed all the input. On the stack we only have the stack start symbol Z left, so we can use the transition from Q1 to Q2, which removes Z from the stack. We are now in an accepting state and our stack is empty. So this non-deterministic pushdown automaton indeed accepts the word ABBA. It does so with respect to acceptance in final states, and it also does so with respect to acceptance in empty stack. Next we will look at the reverse transformation. We will transform non-deterministic pushdown automata into equivalent context-free grammars. So let M be a non-deterministic pushdown automaton. As a first step of our transformation into a context-free grammar, we transform M into an automaton with the following property. It has a single final state, and this final state is reachable if and only if the stack is empty. We have already seen how this transformation can be achieved. This is the transformation from acceptance with a final state to acceptance with an empty stack. So once we have such an automaton, we proceed as follows. We define a grammar. The terminal symbols of the grammar are the input letters of our automaton. The variables of our grammar are these triples. They consist of a state of the automaton, a letter from the stack alphabet, and again a state of the automaton. The starting variable of our grammar is the triple consisting of the starting state of the automaton, the initial stack start symbol, and the final state of our automaton. Now, what's the intuition about these variables? The intuition is that a variable of the form qbq' allows to derive a word w if and only if in our automaton we have a computation of this form, namely if we start in state q with input w and stack content b, there is a computation to the state q' that consumes all the input w and empties the stack. In other words, there is a path from q to q' that consumes the input w and removes b from the stack. And it does not only remove b, but also everything generated from b. It completely empties the stack. Now, what are the rules of our grammar? The rules are defined as follows. Whenever we have a transition in our automaton from a state q to q' with input alpha, so alpha can be an input letter or lambda, and this transition removes a stack symbol b from the stack, then we add in the grammar a rule from the variable qbq'. We can rewrite this variable to alpha. So in the automaton, the alpha plays the role of the input. In the grammar, the alpha plays the role of the output, what is generated. So we see here that we have a transition from q to q' while removing b from the stack. And that's also the intention of this variable. We have from q to q' while removing b from the stack, we can produce alpha. That's the intuition behind the variables. Now, if we have in the automaton a transition of this form, so a transition from a state q to q' with input alpha, and the stack symbol b is replaced by c1 up to cn, where n is at least 1. So now the b is not removed, but replaced by c1 up to cn. Then we add these rules to our grammar for every r1 up to rn states of our automaton. So we add a lot of rules to our grammar for all possible assignments of states q to r1 up to rn. So how do these rules look? The variable qbrn can be rewritten to alpha, q' c1 r1, r1 c2 r2, and so on, rn minus 1 cn rn. So what's the idea here? If we take a transition from q to q' with input alpha, that we see here, we take a transition, we change the state from q to q'. We don't have input alpha in the grammar, but we produce alpha in the grammar. And now the variable on the left says that we go from q' to rn while removing b from the stack. Now if we take this transition, then b is replaced by c1 up to cn. So if we want to empty the stack, then we now have to remove all of these c's from the stack. We have to remove c1, c2 up to cn. And that is indicated by these variables. Now that b is replaced by c1 up to cn, we now have to go from q' to some state r1 while removing the topmost symbol c1 from the stack. And now we have arrived in state r1. The c1 is removed. And from R1 we have to go to a state R2 while removing C2 from the stack, and so on. Now, it can be shown that the language generated by this grammar is precisely the language that is accepted by the automaton. I think this will become easier to understand if we look at an example. So let's transform this pushdown automaton into a context-free grammar. As a first step, we have to make sure that the final state can only be reached if and only if the stack is empty. Now we have seen how this can be done. We have seen the transformation from acceptance with final states to acceptance with an empty stack. Here actually a simpler transformation suffices, because if we inspect this automaton, then we see that the stack start symbol 0 always remains at the bottom of the stack. It's never replaced nor removed, and nowhere else a 0 is added. So we don't need a fresh symbol for marking the bottom of the stack. So it suffices to use a fresh state for emptying the stack. Here we only add ones on top of the stack, so this fresh state only has to remove ones. And we have to have transitions which remove the 0 from the bottom of the stack if we reach the bottom. So what do we do? From our old final state, we add a transition that removes the 0 from the bottom of the stack and switches to our new final state. So now we switch to the final state when the stack is really empty. Or if there are still ones on the stack, then we switch to Q2. Q2 removes all the ones. And if there's only 0 left on the stack, then we remove the 0 and we go to our final state. So this automaton accepts the same language as our original automaton, but now it reaches the final state if and only if the stack is empty. So now we transform this automaton into a context-free grammar. We have to translate every transition in the automaton in a number of rules in the grammar. So we start with this transition highlighted in red from Q0 to Q1 with input letter A, and the topmost stack symbol 0 is replaced by 1, 0. This gives rise to grammar rules of the form Q0, 0, and then some state, let's call it R2, rewrites to A and then two variables of our grammar, the first Q1, 1R, and the second R1, 0, R2. And this red R2, R1 should be assigned with states from our automaton. So we have one such rule for every possible assignment of a state of our automaton to R1 and R2. There are 4 states, so we have 2 variables, each can have 4 different assignments, so we get 16 instantiations of this rule. Now, what does this rule mean? It means if from state Q0 with a 0 on the stack, we want to go to some state R2, and this could be any of the states. Then how can we do this? If we use this transition, then we can produce an output letter A. We have switched now the state to Q1. Now instead of starting our path from Q0, we start the path from Q1. From Q1 we go via the stack symbol 1 to some intermediate state R1, and then once the stack symbol 1 has been removed and we are on R1, then from R1 we go via the stack symbol 0 to our final destination R2. So similarly, we translate this transition again from Q0 to Q1, now with input C, and a 1 on the stack is replaced by 1, 1. So again we get a rule or a scheme of rules of the form Q0, 1, R2 can be rewritten to C, Q1 because we switch to Q1. Now the topmost stack symbol is a 1. We have an intermediate state R1, and then from R1 we go via the stack symbol 1 to our final destination R2. Now if we translate this transition, then we start in Q1. So if from Q1 we want to go with a stack content 1 to some arbitrary state, now we don't need intermediate states because the stack symbol is replaced by a single symbol. So we only need one state R1. So if from Q1 we want to go via stack 1 to R1, then we can produce a C. And after switching from Q1 to Q0, we now have to go from Q0 with stack content 1 to our destination R1. Now we translate these lambda transitions, and they are easier to translate because the lambda transitions, the only thing that happens is that we're producing the output. We don't replace, we don't have any variables in the right hand side of the rule. So this lambda transition is translated to a rule. From Q1, we can go to Q1 with the stack content 1 while producing a B. So from Q1 we can go to Q1 with stack content 1 and produce a B. And similar for this transition, we can go from Q1 to Q3 with stack content 0 while producing lambda. The same for this, we go from Q1 to Q2 with stack content 1, the 1 is removed, and we produce lambda. Likewise for this, from Q2 we go to Q2, we produce lambda, and we have a stack content 1, which is removed. And finally, this transition is translated into from Q2 we go to Q3 with stack content 0, and we produce lambda. Now let's have a look how this grammar works in practice. So let's try to use this grammar in order to simulate the computation of this automaton. The starting variable of our grammar is the starting state of the automaton together with the stack start symbol 0 and the final state of the automaton. Now let's have a look at the computation of the automaton. We start with state Q0, the input ACCB, and the stack only consisting of the stack start symbol. Now we take a transition to Q1 from Q0 to Q1 with input A. So our stack symbol 0 is replaced by 1, 0. Now we have a 1, 0 on the stack and the A is consumed. Now we take a transition back to Q0. We consume the C and the 1 on the stack is replaced by 1, so the stack stays the same. From Q0 we go again to Q1, we read the C, and the 1 on top of the stack is replaced by 1, 1. So now this 1 is replaced by 1, 1. Now we are on Q1, we stay in Q1 reading a B, so we take this transition from Q1 to Q1, we read the B, and we remove the topmost symbol 1 from the stack. The topmost symbol 1 is removed. We are in Q1, no more input letters to read, and the stack still contains 1, 0. We take a transition to Q2, so from Q1 to Q2 without consuming input and removing a 1 from the stack. Now we're in Q2, we take a transition to Q3, we remove the 0 from the stack, so the stack is now empty and the input is empty. We are in a final state with empty stack and empty input. So the word ACCB is accepted by our automaton, and now we want to use our grammar in order to generate the word ACCB. We start with our starting variable, Q0, 0, Q3. So we want to go from Q0 with stack content 0 to Q3 while producing the word ACCB. We go from Q0 with stack content 0 to Q3 and we read an input letter A. Now, what transition of our automaton do we take? We take this transition. And what grammar rule does this correspond to? So, from Q0, we switch to Q1 and we have read an A. So reading an A now in the grammar corresponds to producing an A. Since we have switched from Q0 to Q1, we now have Q1 instead of Q0 in the first variable. Now we have two variables because our stack has increased. The 0 has been replaced by 1 0. So we have now two variables here. One that has to remove the stack symbol 1, and the second variable has to remove the stack symbol 0. So now the question is, from Q1 via stack symbol 1 we have to go to some intermediate state, and then from the same intermediate state we have to go to Q3. So what intermediate state should we fill here? And the point is that we can see this intermediate state from the computation of our automaton. The intermediate state that we fill here is the state that the automaton is in as soon as this symbol 1 has been removed from the stack. So here we have our symbol 1. So we now look, where is this removed from the stack? Here it's not yet, not yet, not yet. Now the stack is smaller. Here suddenly, here we have a stack of size 2. And here's the first time that we have a stack of size 1. So it's the state Q0 that, Q2 that we want to fill in this place. And this corresponds to an instance of our rule scheme 1. So if I take this rule scheme and I fill for R2, I fill Q3, and for R1, I fill Q2, then I obtain this rewrite step. Okay, now we have to continue. We have to look, what do we replace this variable by? So we are now in this step. What happens here? From Q1, we switch to Q0, and we have read a C from the input. So now that means we now produce a C. By this step, we produce a C. The Q1 becomes a Q0. So this Q1 is now a Q0. The 1 has been replaced on the stack by a 1 again. So we have only one variable. So we go now, instead of going from Q1 to Q2, we now go from Q0 to Q2 with stack symbol 1. And this corresponds to an instance of rule scheme 3. If we fill for R1 Q2, then we get this rewrite step. Now again we have to replace this variable. So this is, we are now in state Q0, we read a C, and we switch to Q1, and the 1 on the stack is replaced by 1 1. So we will produce a C. We have two variables because we have put two symbols on the stack. So we get this 1 1, that's this new symbols on the stack, 1 1. We now have switched to Q1, so we go from Q1 to, we wanted to go to Q2, we still want to go to Q2. Now we have two symbols on the stack, and again the question is, what is the intermediate state that we have to fill here? So we check, at what point is this 1 removed from the stack? It's immediately removed in the next step, namely when we reach the state Q1. So we have to fill Q1 in this place. So this rewrite step is an instance of the rule 2, where for R2 we fill Q2, and for R1 we fill Q1. Then we get this rewrite step from this to here. Now we have to replace this variable. So we are here in our automaton computation. From Q1 we read a B, and we go to Q1 while removing 1 from the stack. So that's a lambda. We replace the 1 by a lambda. So we have a transition that removes the symbol from the stack. So this is simple. We just use a rule that goes from Q1 to Q1 with stack symbol 1 and produces a B. And that's exactly rule number 4. We go from Q1 to Q1 with stack symbol 1 and we produce a B. Now we again have a variable. We go from Q1 to Q2 with stack content 1. That's here. From Q1 with stack content 1 we go to Q2. And again in this step we remove the 1 from the stack. So whenever we remove a symbol from the stack, that's easy. we just have to look, that's the rule. We go from Q1 with stack content 1 to Q2, and we produce nothing, lambda. And finally we go from Q2 to Q3 with stack content 0, producing nothing. That is this rule. From Q2 with stack content 0 we go to Q3 and we produce nothing. So now our grammar has generated the word ACCB. And the main point here that I wanted to make is that whenever we have a rule with this intermediate states, like here R1 or here R1, then we can look at the computation of our automaton, and the intermediate state that we have to fill is the state where this symbol, the corresponding stack symbol, was removed from the stack. So here the 1 has been put on the stack, and this intermediate state that we had to fill here was the state Q2. That's the state that we have arrived here as soon as the 1 was removed from the stack. The 1 was removed and everything generated from the 1 was removed as well. And likewise in this step, this was here the 1 was put on the stack. What intermediate state that we fill in here? That's the state where this 1 was removed from the stack. That's exactly this Q1. There's also a deterministic variant of pushdown automata. A deterministic pushdown automaton, short DPDA, is a non-deterministic pushdown automaton for which the following conditions hold. First, if we apply the transition function to a state, an input letter or lambda, and the stack symbol b, then this set that we get contains at most one element. So there's at most one transition to choose from. So for every state and every input letter or lambda and every stack symbol b, there's at most one outgoing transition for this input and this stack symbol. But moreover, we want that if we have a state q that has an outgoing lambda transition for a particular stack symbol b, then the state should not at the same time also have an outgoing A transition for the same stack symbol B. The problem here is, if we are in state Q and the next input letter is an A, and on the stack we have a B, then we suddenly have a choice. Either we take this transition reading the letter A, or we take this transition ignoring the input, taking a lambda transition. Because we are on state Q and we have on the stack a B. So also this gives us a non-deterministic choice. And this is also forbidden. If both conditions hold, then the automaton is called deterministic. A language is called deterministic context-free if there exists a deterministic pushdown automaton that accepts the language. And the nice thing about deterministic pushdown automata is that it's very efficient to check whether a word is accepted by the automaton. There's never a non-deterministic choice, so we can simply read the word and we immediately know whether it's accepted or not. And this also means that deterministic context-free languages allow for efficient parsing. Which of the languages shown on this slide is deterministic context-free? Let's start with a to the n, b to the n for n greater equal 0. This language is deterministic context-free. Intuitively, the reason is that we don't have to guess. We push elements while we read A's, and we pop elements from the stack as soon as we start reading B's. So it's clear when there's the transition from A's to B's, and we just have to count that we have the same number of B's as we have A's. Indeed, it's an easy exercise to create a deterministic pushdown automaton for this language. What about this language? So we have W reverse for words W over the alphabet AB, and these words should be non-empty. So basically that's palindromes of even length over the alphabet AB. This language is not deterministic context-free. A pushdown automaton reads this word from left to right, and the pushdown automaton doesn't know where the middle of this word is. the pushdown automaton just sees A's and B's, and it cannot know when to switch from W to W reverse. So it doesn't know when to switch from pushing elements onto the stack to popping elements from the stack. So for this language, it's indeed not possible to create a deterministic pushdown automaton. What about this language? It's very similar, but now we have a letter C in the middle. And indeed, for this language, we can create a deterministic pushdown automaton, because now the C tells us when we have to switch from pushing elements to popping elements. We now know when we switch from W to the reverse of W. And it's a nice exercise to try to create a deterministic pushdown automaton for this language. So in conclusion, we see that not every context-free language is deterministic context-free. And there is a landmark result from the end of the 90s that says, for deterministic pushdown automata, language equality is decidable. So given two deterministic pushdown automata, it is decidable whether they accept the same language. And this really was a landmark result because it was already long known that for non-deterministic pushdown automata it is not decidable, but the proof that it is decidable for deterministic pushdown automata was really difficult and was open for many years.